Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. By putting that dash there, Dmitri was making a bold statement. He said, and I'm paraphrasing here, "Y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka aluminum, Eka being Sanskrit for one. Based on where it's located, I can tell you all about it. First of all, an atom of Eka aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. He predicted other elements that were unknown at the time: scandium, germanium, rhenium. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963.
Every atom has a core, which is made up of at least one positively charged particle called a proton, and in most cases, some number of neutral particles called neutrons. That core is surrounded by negatively charged particles called electrons. The identity of an atom is determined only by the number of protons in its nucleus. Hydrogen is hydrogen because it has just one proton. Carbon is carbon because it has 6. Gold is gold because it has 79, and so on. The cores of atoms tend to stick together, but electrons are free to move. One of the weirdest things about electrons is that we can't exactly say where they are. It's not that we don't have the equipment, it's that this uncertainty is part of our model of the electron. So we can't pinpoint them. Fine. But mostly electrons stay close to their nucleus, as clouds of negative charge density that shift and move with time. How electrons from one atom interact with electrons from another determines almost everything. Atoms can give up their electrons, surrendering them to other atoms, or they can share electrons. And the dynamics of this social network are what make chemistry interesting.